So we shall continue on in our studies here. But I guess before I go on, are there any questions relating to the material that's been covered? So, chi-square tests, t-tests, all that, that's okay? Everyone had a good Thanksgiving, I'm hoping? Okay. And we haven't completely forgotten everything? Okay. The lab assignment go okay? Not really a lab, just more so a reading assignment. Questions on that? Okay. I guess that's fine. All right. So, well, today we will talk about ANOVA. So this is chapter 11, and we're going to learn ANOVA, and we will learn just the simplest form of ANOVA, which is one-way ANOVA. So, like many of the different topics we encounter in this course, you can learn a lot more. So, as for ANOVA, you can take an entire course based on ANOVA and go much deeper. We're going to spend just this week's lecture on the topic, and we're just going to learn the most basic form, which is one-way ANOVA. I'll make a slight mention or brief mention of, I guess, more complicated forms of ANOVA. Next week, we are going to cover, so let me just talk a little bit about, I guess, the last few weeks of our class. So this week we'll cover ANOVA. Next week I will cover chapter 12, which is regression. Okay. You have a quiz next week, which will cover basically chapters 9, 10, 11. I'm trying to think. Oh, I might throw in a t-test in there. Okay. So you'll have a quiz next week, and then after next week will be the final exam. So I won't be able to have your quizzes graded and returned to you before the final. So what I'll do is you guys will take the quizzes next week, and then I'll pass out answer keys to the quiz so you can kind of see correct answers. I think, so at the end of today's lecture, at the end of chapter 11, I'm going to just do kind of like a brief, well, with whatever time we have left, I'll start to do a review, okay? And then next week, we'll cover new material from chapter 12, and then whatever time we have left there, I'll also do a little bit of review as well. So just we're preparing. Yes?
The final is cumulative?
Final is cumulative, but heavy focus on stuff from after the midterm. So not too much stuff from before. Okay. All right. Any other questions as to just what administrative stuff of the course? At the end of the course, if you want your grades sent over, you got to contact the records office. Their information's on the website. You can just ask them to send a transcript over to wherever it needs to be sent.
Do you know when they close and you need transcripts right away?
Oh, close for the holiday? Oh. I want to say the last week of December, so I would say they might be open. They may or may not be open Christmas Eve.
Okay.
But pretty much from then to, I would say, the new year, they're probably closed, I think, their application. So.
And grades will be posted like how many days?
So, give me a few days to grade the final, and I'll get them posted. So, your final exam is what day? 18th. Yeah, so it's a tight race, huh? Because Christmas is one week after the final. So, okay. Well, yeah. So the final is on the 18th. Yeah, give me. Probably get them posted by following Monday. And then they should have it next day, so, okay. But we'll all, everyone's busy, yes?
Is it going to be multiple choice also?
Yeah, the final is going to be all multiple choice, all Scantron. Okay. Yes?
What are you study then?
I will not have a study guide, like, I'll have kind of the list of all the topics you need to know, but I don't have a prepared study guide or practice. Sorry. Okay. But we'll talk about that stuff. Okay. All right. So let's talk chapter 11, ANOVA, one-way ANOVA. Okay, so one-way ANOVA. ANOVA stands for Analysis of Variance. Okay, so the ANOVA, ANOVA, and we use this when we have a numeric variable as our response, and we have a categorical variable to make different groups. So we might call this our predictor, or we'll just categorical variable as our predictor, but we just have different groups. At this point, it doesn't sound like ANOVA is very different from a t-test. In a t-test, you have a numeric variable as a response, and you have two groups, which is essentially a categorical variable. Okay, so if we said, is there a difference between the mean IQs of males and females? Your response would be the IQ, and your predictor would be the sex, male or female. Okay. The difference between ANOVA and a t-test is that t-tests, you can only have two groups. So your categorical variable, you're only allowed to split into two groups. You have a control and a treatment group, where you have this group and that group. Okay, you can only have two groups. With ANOVA, you are allowed more than two groups. More than two groups, all right, versus t-test, we only have two groups. So, for example, a situation where we have multiple treatments, okay? So, in maybe you want to know what kind of I don't know, the different dog foods affect how much weight a dog gains or something, okay? So let's say you have, and somehow you have a bunch of dogs to watch after. Okay, but maybe you have, you put different dogs on different diets, and so you might have 4 diets. Okay, so you have diet A, diet B, diet C, and diet D. Okay, so maybe, you know, diet A, they're getting canned dog food, and canned and kibble, and diet B is kibble only, and C is, I don't know, some other brand, whatever. Okay, we can have different different groups here. Okay, and we might want to know, is there a difference between the diets? Okay. Is there a difference between the diets, or conversely, is there no difference, or could all the diets be seen as the same? Could all the diets have the same effect? With a t-test, we might be, you know, if we did not know ANOVA, we might be tempted to just do a bunch of t-tests, okay? So, let me call this the naive approach of multiple t-tests. And there's nothing inherently wrong about this approach, except we will encounter some problems here, okay? So we could do multiple t-tests. So test 1 could be diet A versus diet B. Okay, and we would, you know, our null hypothesis is that the mean of diet A is that equal to the mean of diet B, versus that it's different, etc., etc. Okay? And then we could have the other test. We could have you know, A versus C, A versus D, B versus C, B versus D, and C versus D. Okay? And I could do 6 different tests to see if there's a difference between any of the 4 diets, okay? Or any pairs of the diets, I should say. Okay. Do you guys see any problem with doing this, other than it being a bit of work? Okay, so yeah, 6 tests, that's actually not too much work, okay? And it's very simple with a computer. So the problem isn't that you have to do a whole bunch of tests, okay? But there is a problem with having to do many tests, and that is the risk of a type 1 error, okay? So let's say we do each of these tests with alpha equal to 0.05. What is the probability of a type 1 error when I did test 1? what's a type 1 error again?
Rejecting the null when the null is true.
Yeah. So what is the probability that we think there's a difference between diet A and diet B when in fact there is no difference? Yeah. There's a 5% chance, okay, that we conclude there's a difference when in fact there is no difference. And there's also a 5% chance for every single one of these tests. Okay. Technically, it's a little bit different, but okay, so every time I run a test, do a t-test, there is a 0.05 probability of a type 1 error. And so the question is, what's the probability I get through all 6 tests without having made an error? Okay. It's much higher, okay? Or it's getting the probability of committing a type 1 error at least once during our series of 6 tests is higher than when we perform only one test, okay? So, with 6 tests, it becomes more likely for us to make a type 1 error. And there's no good solution to this. Okay. People have different ideas. One is reducing alpha for any one test, so that overall your overall probability of committing a type 1 error is low. But we don't have a good solution. Okay, not yet at least. Okay, this is the problem of multiple comparisons. There's no good solution if we're going to look at every pair at a time. Okay, so every possible pair, we don't have a good solution. One possible way to address this is through ANOVA. Okay, but ANOVA has its own weaknesses. All right? But with ANOVA, we're going to compare all 4 groups, or in this case, all 4 diets, or however many groups you have. We'll compare them all at once. The drawback, though, with ANOVA is that your alternative hypothesis is always going to be non-directional if you have more than 2 groups. So if you have 3 groups or 4 groups or whatever, your alternative hypothesis is always non-directional. And it's, at most you can say is that at least one of the groups is different. Okay? So either you have no evidence that any group is different, or at least one of the groups is different. But ANOVA will not be able to tell you which group is the one that's different. Okay? By looking at the data, you might have a suspicion as to which group is the different group, but ANOVA itself will not be able to tell you which group is the one that's different. Okay, so let's take a look here. Okay, so we'll use this data from the book as our running example here. Okay. So here we have 3 diets. Okay, and we gave these to different lambs, and we measured how much weight the lambs gained. Okay. So under diet 1, we only had 3 lambs, and this is the amount of weight they gained. And those were the weight gains under diet 2, and under diet 3, this is what we have. Just slide this up. Alright, so we are learning one-way ANOVA. And with one-way ANOVA, well, we have a few different ways of writing our hypotheses. Is that with one-way ANOVA, we are going to say that the mean of group 1 is equal to the mean of group 2 equal to the mean of group 3. Okay? Or that the respective populations of each group are all the same. Okay? So all of the respective populations have the same. And the alternative is that at least one of the means is different. Let me say alternative formulation, okay? Okay, and in the alternative formulation, we're saying each value observed, y, can be thought of as mu, which would be, let me just write this. This is the alternative formulation. This would be the mean of everything, okay? So in our case, we have the amount of weight that lambs gain under 3 different diets. In our situation, in this alternate formulation, this would be the mean weight gain of all lambs. Okay, whether they're on diet 1, diet 2, or diet 3, this is the mean weight gain of all lambs. So maybe the mean weight gain is whatever, 13 pounds or something. Tau, there's there's a different tau. This is the effect of the treatment. So that means we're saying if you are in diet 1, maybe you gain an additional pound versus the average. Or if you're in diet 2, maybe you gain less weight versus the average. Or diet 3, you gain, whatever, 2.2 pounds less than the average. So we're saying that the overall, each number you observe is due to the mean of everything plus the effect of being in a particular group or treatment. And this is the residual. This is just anything left over that cannot be accounted for by the model. It's just everybody's different. So people who are all on the same diet, they're not going to gain the same amount. Each individual's difference is called the residual. Does this alternate formulation kind of make sense? Kind of, maybe? Okay. So, with the null hypothesis, with one-way ANOVA, the simple way is just to say that the means are all equal. Okay? We have this alternative formulation for situations, I guess, more complicated than one-way ANOVA. With one-way ANOVA, this works, okay? But with, I guess, more complicated forms of ANOVA, this simple formulation starts to get more messy. So we have this alternative formulation, and the null hypothesis is that the tau, the effect of each treatment, are all the same, and that is that they essentially have no effect. That there's essentially no difference of being in diet 1 than there is to being in diet 2 than there is to being in diet 3. Yes?
So you use the alternate formulation when you're not doing a one-way.
Well, you can use the alternate formulation for one-way ANOVA, okay? It's just that with one-way ANOVA, this formulation is probably easier and easier to understand, okay? It's just that when you have more complicated ANOVA, this way doesn't really work anymore, and so you would have to go the alternate formulation. But the alternate formulation works for one-way ANOVA just as well. Okay, so here we're saying that there's essentially no difference of being in group 1 as there is to being in group 2 or being in group 3, okay? And the alternative is that at least one tau is not 0. So let me just so we'll start off with all the mu's are the same, or at least one of the means is different. Okay, let's look at our data, and we'll make some summary statistics, okay? So each group I'm going to find the mean, the standard deviation, and also write the size, okay? So the size is the easiest. There's 3 in that group, 5 in this one, and 4 in that one. And as for the means, So I just add up and divide by 3, and I would get 11, 15, and 12. And the standard deviations, I won't make you do it, but you know how to find the standard deviation of a list of numbers. And that's all we do here. And I'm using the example in the book, so they've calculated the standard deviations for us. And this is what I have. We have a number called y double bar, which is known as the grand mean. The grand mean is found by not taking the average of 11, 15, and 12. Okay? It is found by adding up all the numbers that we have. So in this case, we have 12 numbers. We add them all up, and we divide by 12. So add up all the numbers, in all groups, and divide by total, how many numbers we have in total. So one way to do this is if we have the raw numbers, we can add them all up. But if we don't, and let's say we're given only the summary numbers, by seeing the sample size of this group and the mean of this group, we know that the total of these three numbers would be 3 times 11, or 33. Is that okay? So one way to get the total number, sum of all numbers in all groups, is we would add up n times the y bars for each group. Okay? And we would divide by the sum of all the n's. So I would do 3 times 11 plus 5 times 15 plus 4 times 12. Divided by 3 plus 5 plus 4. And this would end up being 156 divided by 12, which gives me 13. So my grand mean, my double bar, is 13.
So instead of actually using the data, you're sort of using this an average of the data?
Yeah, well, we could use the data. We could add up all 12 numbers and divide by 12. But sometimes, or a lot of times, people don't give you the actual data values themselves. So you might look at, like in a published study, they might give you the mean and how many people. Okay? So if you're only given the mean and the number of people, you can kind of reverse calculate the grand mean by doing 11 times 3, 15 times 5, and 12 times 4. And then adding that up and dividing by 12. Is that okay? So let me move this, and let me just create a Okay, so I'm going to create a dot plot of diet 1, diet 2, and diet 3. Okay? So under diet 1, we have one lamb that gained 8 pounds, one that gained 16, hopefully this lines up, and one that gains 9. And under diet 2, we have 9, can I copy these from Michelle? Yeah. 9, 16, 21, 11, and 18. And then under diet 3, we have 15, 10, 17, and 6. And let me also draw where the mean of each group is and the grand mean. Okay? So this line, this represents the grand mean. And the smaller line is the mean of each group. So the mean can be thought of as the balancing point, and it kind of looks like if this were a seesaw and it would be balanced right here. Okay, or we put all 5 of these points on a seesaw, then it would be balanced right there. Alright, and so the question is, what we notice is that the 3 groups have different group means from each other, okay, at least in our data. And the question is, could these different group means be a result of just random chance, or does our data indicate that the diets could be partially responsible for, or that, I'm sorry, could the group means be different from random chance alone, or does the diet indicate, does the data indicate that the diets are at least partially responsible? So does the data tell us that we have evidence that the diets make a difference? That's what we're asking. Or do we not have enough evidence to say that, and we just have to conclude that these differences could be a result of random chance alone? That's what we wanted. So from looking at this, what do you guys think? Well, it's hard to judge. It's hard to judge, okay? But it seems like there seems to be quite a bit of spread in how much weight a sheep or a lamb might gain. And so I think it would be hard to say that these differences between the group means are definitely a result of the diet. But we'll see what the data says. Okay. So again, the null hypothesis we want to know. So if the null hypothesis is true, then the differences we see between the group means chance alone. And if the alternative is true, then the diets make a difference. Plus there is random effects. Causes to see the different fruits. So that's what's happening in real life, and what we're doing is we're just using our data to see if we have evidence that the null hypothesis might not be true. Does our data indicate that the null hypothesis is false, and that the alternative is true? So either it does or it doesn't, okay? We either have enough evidence to say the null is false, or we don't have enough evidence. Okay? And if we say the null is false, then that means the alternative must be true. Okay. So let's sorry, is it okay that I'm erasing this? I already started it. Alright, so ANOVA is analysis of variance. Do you guys remember the definition of variance, or what is variance? As a concept, what is variance then? Not necessarily the formula definition of variance, but okay, what about just variation in general? What is variation?
How stuff is different from everything.
Okay, so variation is just the fact that everybody's different, right? That's what makes life wonderful and possibly frustrating, but everybody's different, okay? And we say there's variation, okay? And variance, or variation in a numeric sense, talks about how things are different from the mean, okay? And what we're doing is we square that difference from the mean, and we kind of take an average. So the overall variance of a set of numbers is can be thought of as like the average squared difference from the mean. Okay, so if you recall, the formula for variance, well, formula for the standard deviation is the square root of the variance. Do you guys remember that?
Mm-hmm.
Okay, so I'm just going to do the formula for the standard deviation, but without the square root. Okay, so recall formula. It's not how you spell formula. Formula for variance is that we take each each value, and we subtract off the mean, and we square that difference.